Yo, 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 yo. I gotta keep it low for show. This is problem 2500 to delete greatest value in each row. Um, yeah, so let's go ahead and get right into this problem. So you're given an m by n matrix grid consisting of positive integers. Perform the following operation until grid becomes empty. You're going to delete the element with the greatest value from each row. If multiple such elements exist, delete any of them. Add the maximum of the deleted elements to the answer. Note that the number of columns decreases by 1 after each operation. Return the answer after performing the operations described above. Okay, so in this first problem example, we have this box, and I'm going to change this to lines and grids because I don't like it like this. So we have this box with 2 by 3. Okay, so we have this 2 by 3 box. We have values 1, 2, and 4, and 3, 3, and 1. Well, the maximum value in the first row is 4, and the maximum value in the second row is either of these threes, but we'll just say it's this 3. When you delete both of those, you delete a 4, you delete a 3. The maximum value that you delete is 4, so to your answer, you get plus 4, and that leads to this new 2 by 2 system of 1, 2, and 3, 1. Now again, the maximum value in the first row is 2. The maximum value in the second row is 3. And the maximum value that you delete from 2 and 3 is 3. So you add 3 to your solution. And then finally, you have this 1 by 1 array of 1 and 1. The maximum value in the first row is 1. The maximum value in the second row is 1. The maximum of those maximum is 1, so you have plus 1. So your final answer is 8. With this thing, there's only one row, one value. You delete the 10, you get rid of it. Pretty simple. Okay. So I guess what we should do is make a bigger example, a slightly bigger example. Let's do a 4 by 3 example. And then I'm just going to make up random values. 7, 8, 6, 7, 5, 3, 0, 9, 8, 6, 7, 5, 3, 0, 9. What's another popular number? Let's do odd prime numbers. It's 1 prime. I don't know. 1, 2, 3, 5, 7. Oh, I don't like that though because it's strictly increasing. I don't want to do that. 2, 7, 3, 5. Okay. So here's a random example. Now, what are we going to end up doing? We're going to end up deleting 8, 9, and 7. Right, so I'm going to use different colors to associate each iteration. Right, so there's this first iteration. This is going to have 4 iterations, right, because there's width of 4. So this is the first iteration. All right, we'll have a second iteration, third, and the fourth. All right, so those will be the first values that we delete. And then we're going to delete 7, 3, and 5. So that's the second iteration. And then in the third iteration, we'll delete 6, 1, and 3. That's what's going to occur in the third iteration. And then finally, in the fourth iteration, we'll delete 5, 0, and 2. So why am I using this multicolor scheme? What's the point I'm trying to articulate? What's the reasoning? Well, you know, I guess, should have mentioned this prior, but, you know, the simple solution here would be to just look at all the values in each row for the number of columns, right? So you'd have to look at all the rows and columns for each column, right? Because there's number of column operations that we have to do, right? There's 4 columns in the system, so we have to go through the system 4 times, right? So that would be the simplest solution. So you'd have to look at all rows and columns, right? You have to look at each row for each column, to find the maximum value, and then you'd have to keep doing that each time that you run this problem. So you'd have to do that column times. So that's row times column squared. Now we have what? How is this problem given? We have m by m, so m rows, n columns. So this would be an m by n squared algorithm, right? So that's not going to be efficient enough. What we could do instead is, well, I guess, what if we could pre-compute the maximum values, the second maximum values, the third maximum values, the fourth maximum values, and so on and so forth. What I'm basically saying is, what if we sorted this system with respect to each row? Then you would know, the first thing, because the green value is the first thing to get deleted, right? Then the blue values are the second things to get deleted. And the red values are the third things to get deleted. And the yellow values are the fourth things to get deleted. And those are deleted based on, we make the decision by the quantity of the value, right? So we delete the biggest values, then the second biggest values of each row, and the third biggest values of each row. So if I was to sort this system with respect to the rows, what would that look like? So it's a 3 by 4. So you have 8, 9, and 7. And then 7, 3, and 5. And then 6, 1, and 3. And then the last row sorted. Let's do it in that order so it makes more sense. So the first row is 8, 7, 6, 5 if it was sorted. If we sorted the second row, it would be 9, 3, 1, 0. And if we sorted the last row, it would be 7, 5, 3, 2. Right. And then what do you notice about the system? Well, let's just map these colorings appropriately. So let's first map the green values. So 8 is green, 9 is green, 7 is green, 7 is blue, 3 is blue, 5 is blue, 6 is red, 1 is red, 3 is red, and then 5 is yellow, 8 is yellow, 0 is yellow. So what you notice here, right, is, well, it makes sense, right? Because the first things we delete are the greatest values in each column. In each row. The second thing we delete is the second greatest value in each row. So when we have this system where we figure out what we delete, if we first sort the system with respect to the rows, we get a very clear and obvious approach where we would just look at the max of this column, and 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 the problem will be done. So what's the runtime of that? Well, in order to sort each of these rows, so it's n log n. All right, so that'll take n log n operations to sort each row. Right, and there's m rows, so it's m times n log n operations. And then we have to look at each row, each column. So this is the first operation to sort each row, right? Because we have to sort for each row, we have to sort it with respect to columns. So that's m times n log n operations. And then we have to look at each column pivot and find the max value. So we have to look at each column, right? And then we have to look at all the values in the column to figure out what the maximum giving value would be, right? So this one would provide 9. Right, what's the maximum value in this column, right? Because this would correspond, the column corresponds to all the values you would delete in one iteration, right? So the column gives you all the values you would delete in one iteration, and the maximum value of that column is what's going to get added to your score, right? Because if we looked at this problem and we were to play this sorting game here with this problem, just to quickly articulate my point, I'm kind of all over the place today. 3, 3, 1, right? This would be the system sorted, so we know we'd add 4 here because that's the maximum value in the column. We'd add 3 here because that's the maximum value in the column. We'd add 1 here because that's the maximum value in the column, and look, it's the same thing as here, right? So we'd have to look at each column, all n columns, and look at all the row values to find the maximum value. So that's each column, all the row values in the column, n times n. So we've taken our solution from, right, we were originally at, we'd have to look at each row and each column for the number of columns, or remember columns times n. So we've gone from an m times n squared approach to m times n log n plus n times m. This is also equal to m times n 1 plus log of n. Apparently I can't do simple algebra anymore. And then this is just scales. Yeah, it's fine like that, I guess. Right, so this is m times n, 1 plus log of n. If you really wanted to make this cute, you could say, okay, this is m times n log n. Right, so we've taken this extra factor of n and turned it into log n by doing this approach. So basically, what's the way that we do this problem? Well, the first thing we do is we sort rows, and then we return the sum of the maximum of each column. Right. Okay. So let's go ahead and do that. So the first thing we'll do is we'll look at each row in the grid, and then we'll just sort it in place. And then we're just going to return the sum of what? Well, we want the maximum value from the column. Okay, so how are we going to do this? So this is going to get a little bit messy. So how do we get the column of the array? So we could say we look at the row that we're currently looking at, or the column we're currently, because we're going to look at each column and make this decision. So we'll call that C. So we're going to look at each column in range. How many columns are there? That's the length of the grid at 0. Okay. And to find the maximum value in there, we'll do the grid at the row for row in range length of grid. And I'll just put this down here. It looks ugly, but at least you'll be able to see it. And then I'll just, still a 2-line solution. Not too worried about it. Okay. So let's run that. Could be an issue here, right? Because I'm doing a lot of things on one line. All right, let's move this up then. Let's submit. There you go. So what's the runtime of this? So for time complexity, we know that we have time and space complexity. We know what? What do we know? We don't know very much. Apparently, I don't know very much at all. So if n equals the length of grid, m equals the length of grid, so that's the number of rows. Right, and then we said that n equals the length of grid 0, which is the number of columns. For time, well, we have to sort each row, right? And there are m rows, so we have to look at each row, and we have to sort it with each row, and row's length is the number of columns, so that's n log n operations to sort. And then we have to look at each column and look at all the row values at that column to find the maximum one and return the sum of that. So this is just that. And then for space, well, let's just assume that this is we could do an in-place n log n sort here, like with in-place heap sort or something like that. So that would be constant space. And then this would also be constant space, right? Because we're not adding any variables. We're just accumulating a sum, which I guess is dependent on the number of rows, but we're not going to play that complex game. So we'll call that O of 1. And this is O of m times n log n. Okay. All right, guys. Peace out. Thank you for watching this short video.